DSL and cable has brought broadband into our homes for over 25 years, transforming the way we work, learn, and play. Now fiber optics is paving the way for an even faster and more reliable future. This is the first of 3 videos talking about how these technologies work. In this video, we'll talk about DSL. Now here we're going to be talking about the different types of DSL lines. First we have ADSL, which stands for Asymmetric Digital Subscriber Line. Now here we have 3 types of ADSL lines: ADSL, ADSL2, and ADSL2 Plus. Now both ADSL and ADSL2 both have the same frequency of 1.1 megahertz, but the download speed is different: 8 megabits per second for ADSL and 12 megabits per second for ADSL2. The reason for this difference in speed is because of better error correction and coding techniques for ADSL2 versus ADSL1. Now the upload speed for both ADSL and ADSL2 is 1 megabits per second, and the difference in speed between download and upload is simply because they're asymmetric. So if they were symmetric, you would have the same speed download and upload. So you may have 8 megabits per second down and 8 megabits per second up, or 12 megabits per second down and 12 megabits per second up. These ADSL lines are configured that way because most people download more than they upload. So that's the reason they're configured this way. Now for ADSL2 Plus, we have a frequency of 2.2 megahertz, which is double the frequency of ADSL2. And the download speed is also double, from 12 megabits per second to 24 megabits per second. Now the upload speed is still 1 megabit. So ADSL2 Plus is also asymmetric. Now for VDSL, which stands for Very High Frequency Digital Subscriber Line, VDSL can be both. It can be asymmetric or symmetric. Now for VDSL, which stands for Very High Frequency Digital Subscriber Line, for VDSL got a frequency of 12 megahertz and VDSL2 got a frequency of 30 megahertz. For the download speed, for VDSL we have 52 megabits per second, and for VDSL2 we have 100 megabits per second. And the reason VDSL2 have a higher speed is because it has a higher frequency. For the upload, we have 16 megabits per second for VDSL and 40 megabits per second for VDSL2. Both VDSL and VDSL2 are both set up in an asymmetric format versus symmetric, even though VDSL can be both. But most of the time, ISPs would choose asymmetric. Now here's how your DSL line will be connected to the internet. Now we have the internet here, and this is a fiber optic cable going in to a DSLAM, and this DSLAM stands for Digital Subscriber Line Access Multiplexer. Now on this side of the DSLAM we have a router interface in order to communicate with the internet, and on this side of the DSLAM we have a modem interface in order to communicate with the DSL modem. Now this is twisted pair in here. I know it doesn't look like twisted pair, I just drew it this way for simplicity, but this is a regular telephone wire that you will have in your home. Now I have T and R here. T stands for tip and R stands for ring. This is how the telephone industry labeled the 2 wires. One called a tip and the other one called a ring. Now we have a frequency of 30 megahertz sent into the DSLAM. This is actually the frequency of VDSL2. So we're going to be using a VDSL2 line as our example for this today. As I said in the last slide, I'm using a frequency of 30 megahertz to send from the DSLAM to the modem. But we just can't send 30 megahertz like that along this twisted pair cable. So what we have here is what is taking place within this cable. Let me explain. We're sending a frequency of 30 megahertz from the DSLAM to the modem. We can't send it just as a whole 30 megahertz. We have to break it up. So we break it up into 4 kilohertz sections from 0 hertz all the way down to 30 megahertz. This is 30 million hertz, which is 30 megahertz. I divide that by 4.3124 kilohertz. That is 4 kilohertz. I just round this off, but it's actually 4.3124 kilohertz. So I divide 30 million hertz by that. I get 6,957 4 kilohertz channels. So I have 6,957 4 kilohertz channels from 0 hertz all the way down to 30 megahertz. Now the very first 4 kilohertz channel between the DSLAM and the modem is used for the telephone from 0 hertz to 4 kilohertz. Now from 4 kilohertz right through to 25 kilohertz, as I have written here, is called the guard band. This prevents any interference between the telephone line and the upstream from the modem back to the DSLAM. The upstream occupies this area between 25 kilohertz and 5.2 megahertz. So if you had the phone right next to this, you will get interference. So they have this separation in here to prevent interference between the telephone and the upstream. Now from 5.2 megahertz to 30 megahertz is used for the downstream from the DSLAM to the modem. When you power your modem on, the DSLAM would detect that this modem is on, and the DSLAM will send a 4 kilohertz tone at all of these frequencies between 25 kilohertz and 30 megahertz. When the modem receives these frequencies, it will take a note of the dB level and the signal to noise ratio on all of these 4 kilohertz channels, and it will send this information back to the DSLAM. When the DSLAM receives this information, it will make a note on how much data can be sent on each one of these channels based on the information that it got back from the modem. Now ultimately, the reason this is all being done, the DSLAM is trying to get this 300 megabits of data from the internet through to the modem. So the DSLAM will take the information that it got from the modem regarding the status of the lines, and it will prepare these channels for that data. And how it does this is to use these 4 kilohertz channels and prepare them for modulation of this data. It would base this on the condition of these channels, like how much noise these channels got on them. So based on this information from the modem, the DSLAM would prepare these channels. So let's say, for instance, this very first channel here on the downstream has very little noise. The noise level is extremely low. Usually for the lower frequencies, the noise is also lower, and higher frequencies usually carry more noise because higher frequencies are more susceptible. So here for this low frequency, we are able to send 1024 cam. We have different cam settings. We have from 16 cam, 64 cam, 256, and 1024. 1024 cam would carry the most data. The bigger the number, the more data it carries. You could try to remember it that way. So 1024 cam will carry more data. So we have more data on this very first channel, and also more data on these first two channels here, because the noise level is low, so you can have more data. Now these first two channels will be modulated with 1024 cam. Now this one here will be modulated with 256 cam, because there's more noise on this particular channel, so they had to lower the data rate. So they're using 256 cam here, and the next channel over is using 64 cam because the noise level is even higher. So they use 64 cam, lowering the bit rate. And the very last one here, the bit rate would be the lowest, 16 cam. So you have much more noise on this channel, so you have to lower the bit rate. So once that is done, the DSLAM will send the modem instructions and how to set up is upstream based on the information that the modem had already sent the DSLAM. So the modem would set up the upstream based on that information. It's using 1024 cam for these two, 256 cam and 64 cam. Once that is done, the DSLAM and the modem is synchronized. Before this point, you would have had a flashing synchronization light on the modem because this was a process called training. This is when everything that we've talked about is taking place. That is called training. And once that training is completed and these channels are set up correctly with the right modulation, then that training is completed and you would get a synchronization light on the modem. So at this point, the modem would be ready for data to be sent from the internet through to each one of these channels to the modem, and also to send back from the modem back to the DSLAM. This whole process that we've talked about is called Discrete Multitone Modulation. It's abbreviated as DMT, Discrete Multitone Modulation. Now this is the setup configuration for most DSL lines. You have the DSLAM coming from your ISP, and you have your twisted pair cable coming right to your customer's premises. Now right within the customer's premises, the twisted pair is directly connected to a splitter, and then your phone is connected from one side of that splitter, and then your modem is connected on the other side, and then of course your computer or your Wi-Fi equipment will be connected to the modem. Now inside of this modem, you have a username and password that is given to you by your ISP. You have to enter this information in order to be authenticated by the DSLAM. The DSLAM is what gives you access to the internet when you enter the username and password in the modem. Once this password is validated, you would be given an IP address in the modem. That would be a public IP address, and this is what gives you access to the internet. The purpose of this splitter is supposed to separate your telephone from your modem. Like the frequencies that comes in to the modem is separated from the phone. If you didn't have this splitter, you'll be hearing these frequencies when you use the phone. You'll be hearing those tones come through. It could be quite annoying. And for the modem, whenever you use the phone, this would cause an interruption with the modem. It could actually cause the modem to go out of sync. So it is very important to actually have this splitter. Now, for the DSLAM side, you don't need a splitter at this end for the simple reason that you have the guard band between the telephone and the upstream. So this guard band here replaces the splitter, so you don't need a splitter at the DSLAM side. But you don't have any guard band down here, so you need the splitter. This is Trevor from Telecom Training. If this video was helpful to you and you would like to see more videos like this one, please don't forget to like and subscribe, so that you'll be alerted as soon as our new videos are released. We'll soon be releasing related videos to this one on cable and fiber optics. Thank you for watching, and I'll see you in the next video.